Okay, let's look at a couple of different flux problems here. So in this one, we've got this cube, we've got a charge inside the cube, and we want to calculate the total flux through each side. Now, we could do a really complicated integral. If we did this as a calculus problem, it would be very, very challenging. Or we can just use Gauss's law. If we remember that if we have a closed orientable surface, then the total flux through the entire surface, through everything, is the charge enclosed over epsilon naught. So we know the charge, it's inside the cube, it's enclosed, divided by epsilon naught. This is our total flux through the entire cube. Well, we've got a cube here, all the sides have the same area, so the flux through each face is just the total flux divided by 6, because we have 6 sides. So through each side we have 1/6 of the total, which is that much. Okay. Now that's different from this problem. Here we have similar looking cube, and it's a cube, and a constant electric field. No charge inside the cube. So what's important the whole time we got to remember, the total flux through the entire cube is 0 because there's no charge inside. So if we were asked for what's the total flux, 0. We're done. There's no charge inside. I don't care what E's doing. But that's not what we're asked. We're asked for the flux through each side. So we have to think about directions. Remember, in general, flux is an integral. It's the integral of E dot dA. If we have a constant E and constant A, then flux is magnitude of E times A times the cosine of the angle between E and our normal vector. Flux measures how much of the electric field passes perpendicularly through a surface. So here, if we look, let's call this side the top. E is pointing to the side. The normal vector to the top here would point straight up. So I've drawn that in a little diagram here. E is running right along the surface. E is perpendicular to the normal vector. Or another way of saying that, E is parallel to the surface. So E is not passing through the top. It's running along the top. The flux through the top is 0. Same on the bottom. Same on this front side here and this back side. E is running parallel to all of those. So through the front, the back, the top, and the bottom, the flux would be 0. All the flux is going to happen over here on this left side and on this right side. Now, the good rule of thumb here, if you have a closed surface, flux passing out is positive, flux passing in to a closed surface is negative. So over here on this left side, E is passing into the cube. We call that negative flux. And over here on the right, E is passing back out again. We would call that positive flux. We can think of that in terms of our formula too. E, A, cosine of theta. Or a phi, cosine of phi here. So for that left side, my normal vector, your normal vector on a closed surface always points out from the surface. So E and N, the normal vector, they're really, I wrote here parallel, but they're really anti-parallel. The angle is 180 degrees. Cosine of 180 is -1. So the flux passing through this left side, this side right here, is negative E times A. It's a square, so A is just one side squared. And we get this negative 0.75 Newton meters squared per coulomb. The right side, E points to the right. My normal vector would point to the right. Those are parallel. Cosine of 0 is 1. The flux through this side would be positive 0.75. Exactly the opposite of that one. All the flux that's flowing in over here is flowing back out over there. The total flux is 0. If we were to add up all these sides, we would get 0. Because Q enclosed is 0.